Hello everyone, welcome to the purple classes of the Russ Indica ICE Academy. Desh Badala, Padhai Badlo, and today we will be discussing about again one of the most important topic in the science and technology. This is again going to be a two-part topic, and we will be discussing first of all, it is a topic on nuclear technology and nuclear energy, right? So in this topic, we will be discussing the role of nuclear technology in the power generation, and we will be also discussing regarding our Pokhran, and after that we will be also discussing the issue of nuclear energy throughout the world, and how India is combating all these things. And we will be discussing we'll also discussing about the nuclear supply groups, India civil nuclear deal, and all these points we will be discussing in this session. Actually, in the part 2 also we will be discussing some of the policy aspects. So here we will be discussing some of the technical aspects of the nuclear technology, so that you come to know like how the nuclear energy is produced. Okay, so we will be discussing the technical part of that in this part 1 of the session, and in the part 2 we will be discussing some of the policy aspects, some of the application aspects, and everything in the next session. Okay, so let's start with our topic. So this is Indian economy, science and technology, and we will be discussing the nuclear technology part 1, right? So this is going to be part of our science and technology. And first of all, today we will be focusing on what is the meaning of nuclear energy. Obviously, whenever we talk of nuclear energy is derived from the nucleus of an atom. Okay, that is the energy that is derived from the nucleus of an atom, and whenever this atoms breaks into smaller atoms, it produces energy, and this energy we utilize for variety of purpose. Okay, we all know that atoms are having lot of energy. High speed atoms have lot of energy. You have also heard about the Einstein very famous equation is E is equal to mc square, right? E is equal to mc square, which is again focusing on, which tells about the immense amount of energy that is stored in anything which is traveling at a very high speed. Okay, so this energy we will be harnessing in various aspects at various places. Okay, so there are two type of like process that happens in the nuclear energy, that is nuclear fusion and nuclear fission. Okay, right now in our country and various part of the world, we are utilizing nuclear fission to generate energy from the atoms. Okay, and the heat that is utilized will be utilized for generation of electricity, and also at various other purposes we can utilize. Okay, so we there are a lot of so here what we have written is what components and nuclear reactors are having, since we will be first discussing regarding the energy that is we will be utilizing for generation of electricity. Okay, so this is our main focus of this topic, is that how these nuclear energy generates electricity. So that is why we are being totally discussing this part only in this lecture. Okay, so we have a nuclear reactor, the power plants are being created, and nuclear reactor is there where we do a controlled nuclear fission reaction. Okay, there is a controlled nuclear fission reaction we do, and with this controlled nuclear fission reaction we are able to generate heat energy. That heat energy we utilize for generation of electric energy. Okay, so there are a lot of mechanism is there, so we will be all discussing how this works. Okay, so what is the fuel source that we are utilizing? Obviously, uranium is there. Uranium pellets are there, which we are utilizing as a fuel source, which is utilized in the nuclear reactor in the form of assembly. Okay, fuel rod assembly. Okay, you don't worry about all these things because I have a schematic diagram and pictorial diagram for all these things. Okay, so this uranium pellets and uranium atoms goes fission reaction, and during this fission reaction, this this fission reaction will become so speedy and fast that it get converted into a chain reaction. Okay, so this chain reaction keeps on producing heat energy, and that heat energy we utilize. Okay, so the heat generated by the nuclear fission warms the reactor cooling agent, and cooling agents such as water, liquid, metal, molten state are used to produce steams. Okay, now the steam that is generated by this heat energy helps in running the turbine or moving the turbine, and this turbine is connected to a power generator, and then power generator will able to generate the power and it will be feed into the grid lines. Okay, so what now, since the nuclear fission reaction has to be controlled, it can only be controlled by controlling the amount of neutron that it is releasing. So that is why we also have control rods. Okay, rods of nuclear poison, xenon, that regulate the rate of chain reaction. Okay, so we have to control the chain reaction that is happening inside the nuclear reactor, but otherwise it goes out of control. It may act like a potential bomb, and it can create a havoc at the places where it is there. So Chernobyl you might have heard, 3 Mile Island you might have heard, Fukushima you might be knowing that 2011 because of the tsunami that has came in the Japan, right? So there is a need to properly regulate this whole process, then only controlled heat energy can be generated, which can be utilized for this whole purpose. Okay, so this is how the nuclear fission normally works, right? So nuclear energy is in the form of a nucleus, core of atoms. You know, core of the atoms is made up of proton and neutrons, right? We know protons and neutrons. The nucleus is made of protons and neutrons, and we can utilize the energy that is stored at this nucleus in two ways. Okay, with the help of a fission reaction and with the help of a fusion reaction that we have discussed. Okay, in the fission reaction, the nucleus of the atom is split into various other parts. Okay, and in fusion reaction, nuclei fuses together. Okay, in fission, one nucleus split into various other nucleus, and in fusion, two nucleus get fused into a different. So fusion reaction is still we are not able to control properly, but recently last year the news came from the USA that they have tried to sustain, they are able to sustain the fusion reaction also. Okay, so it is still in R&D phase, but yeah, fission reaction we are able to properly control. Okay, so under the nuclear fission, what happens? The nucleus of an atom is split into two or more smaller nuclei. Okay, they split into nuclei, and whenever they are splitting, they are also releasing energy. So this is only the energy that normally we utilize for that. Okay, so like here you can see we have a neutron. Okay, this is hitting the nucleus of a fissile nucleus, that is uranium, and with this it is splitting them into two smaller nuclei. So while splitting this big nuclei into two smaller nuclei, there is certain heat energy that is generated. This is one part. And if that is happening for all the nuclei, so now from here we get 2-3 more neutrons, they will again attack one bigger nuclei. So this is a chain reaction which comes into place. Okay, so this chain reaction will produce enormous amount of heat energy, Okay, so we know that here we have a nucleus of uranium-235. Okay, U-235 get split into two smaller nuclei. Okay, one is of barium and another one is of krypton. Okay, you might have heard that word krypton, right? And they produces 3 extra neutrons. These 3 extra neutron will again hit 3 nuclei of uranium, and these 3 neutron will further generate 9 neutrons, like that. So this is kind of a chain reaction which gives rise to the enormous amount of heat energy that will be generating. Okay, So each time, okay, here we can see this extra neutron will hit another uranium 235 atom, and this will again split into the krypton and your barium, and further it will release 3 more neutron. Okay, so this will keep on multiplying chain reaction. With this happens within a fraction of seconds. This is a very fast reaction. So if you wanted to control the chain reaction, we have to control the neutrons. The lesser the number of neutrons, so the lesser number of nucleus it will hit, and the process will be slower. Okay, if you keep the neutron fully like open, it will produce enormous amount of energy. Sometimes it goes out of control also. Okay, so each time the reaction occur, there is a release of energy. Every time whenever there is a reaction happening, there is a release of energy in the form of a radiation. Okay, so this energy we utilize to convert the water into steam, and that steam will run the turbine, and turbine will convert the into that turbine is connected with a generator which will convert them into electricity. Okay, so everywhere you know the process is that we have to run a turbine, whether we are getting heat energy from coal, whether we are getting heat energy from solar, from petroleum, whether we are getting heat energy from any other sources, we are converting and we wanted to run the turbine. Okay, if you are running running with hydrogen, so you are again burning it in order to release energy. That energy will be used to convert into steam. Steam will run the turbine, like that. Okay, whatever we are utilizing, this is the main process how the nuclear energy works. So this is the technicality of the nuclear energy. So this is a very big pictorial diagram. You can see over here, this is a neutron which is coming. It is hitting the uranium 235 atom, and this is getting split into smaller nuclei, okay, either of barium or krypton. Okay, then this whole process releases extra neutrons. These extra neutron will hit another uranium 235 atom. So every process is releasing energy over here. So this energy we are utilizing. Okay, this energy we are utilizing, this heat energy we are utilizing for converting water into steam, and this steam will be helpful in running the turbine, and this turbine will be connected to generator, and this generator will be connected to the grid, and yes, electricity will be produced. Okay, now how does a nuclear power plant work? We have talked about the uranium atom. Okay, so what uranium we are utilizing over here? Yeah, so whenever we wanted to utilize the nuclear fuel, normally we talk about the uranium 235. Okay, uranium 235, it is written like that, 235. Okay, so this is utilized especially for the chain reaction, and this is a fuel that we utilizes to produce heat energy through fission. Okay, so this is the heat warms the reactor coolant agent and water, so produce the steam. Okay, so there will be a coolant agent that will be there, so the heat that will be produced will be converted into steam, like that. Okay, so now what the problem is that whenever we take the uranium occurs in two forms. Okay, there are two forms are there that is found throughout the world. Okay, uranium found into the rocks all over the world. Okay, and they have several isotopes are there. Okay, they have atomic numbers same, but they have a mass number is different. Okay, so uranium has two primordial isotopes are there, that is uranium 238 and uranium 235. Okay, and majority of the uranium that is found throughout the world, that is majority is this, and this is found in a very lesser amount, very lesser amount. And since uranium 238 makes majority, and but the problem is that there is a problem is that it cannot produce chain reaction. Okay, it cannot produce chain reaction or fission chain reaction, but uranium 235 is used to produce energy, but the problem is that it is only 1% of the world uranium that we are having. Okay, so now what is the thing that we have to do? Okay, so to make natural uranium more likely to undergo fission, we need to increase the amount of U-35 into the sample. Okay, whatever the uranium that we are getting, if we wanted to make sure that it should have chain reaction, so we have to increase more and more atoms of U-235 in that, then only it is going to create a chain reaction. So how this is going to happen? So this happens by the process of uranium enrichment. You know, this word always comes into the geopolitics. Okay, geopolitics, because of Iran. Okay, because Iran is having enrichment center where Iran is saying that we are enriching the uranium so that we can have a fissile grade for our nuclear power plant. But the countries, P5 countries, they are saying that no, you are enriching the uranium of a weapon grade. Okay, so weapon grade has more U-235, and the uranium-235 which is needed for power generation has to be enriched little bit. Okay, so uranium enrichment is a very important process. The main purpose is that we wanted to increase the amount of 235 in order to sustain chain reaction. Okay, so that it can be effectively utilized as a nuclear fuel up to 3 to 5 years. Okay, right? So this is how it has to be done. So uranium enrichment is one of the most important thing that has to be done. So based on the type of usage, we have to do enrichment of the uranium. Okay, so normally what I told you, we get when we do mining of the uranium, we get natural uranium like this. Natural uranium. So you can see here the red dot points to the uranium-235 and blue dot it is uranium-238. So maximum is uranium-238 and very little amount of uranium-235 is there. Okay, then we try to slowly enrich this. Enrich means we are trying to increase the concentration of 235. Okay, we are trying to increase the concentration of U-235, that is up to 5% of it. Okay, so this is normally utilized for our power generation purposes. Okay, so uranium enrichment, we know that uranium enriched to a concentration above 0.7% but less than 20%, that is called low enriched uranium. That means from 0.7% up to 20%, it is called low enriched uranium. And most of the civil and commercial nuclear reactor, they utilizes around only 3 to 5% of enriched uranium. Okay, this much only enrichment is required for your commercial nuclear reactor. Okay, commercial nuclear reactor. Okay, if you are enriching the uranium more than 20%, U-235 more than 20%, that will be called as highly enriched uranium. Okay, so all highly enriched uranium is a weapon usable. That means above 20% if you are enriching, so they are well above the standard for weapon grade uranium that you are going to have. Okay, right? All highly enriched uranium is a weapon usable, but the lower the enrichment level, the greater the amount of material required to achieve a critical mass. Okay, this is just a technical word. Okay, so here you can see we have done certain enrichment. Now it is more up to 20%, and here we have done more than 90%, and this is highly deadly weapon grade uranium enrichment that we are having. Okay, but we have to only work till here if we are only creating power. Power means electricity. Okay, so this much is that if we wanted to sustain any kind of chain reaction, naturally we are getting this and we are enriching to this to get a sustained mass, sustained number of U235 to have a sustained chain reaction. Now let's do a little comparison about the energy efficiency comparison that we wanted to find out in this nuclear energy. So here they have given a comparison between the coal, oil, natural gas. Okay, so they said that if we take one pellet of uranium pellet which is utilized in our power plant, okay, that is of height 1 inch. Okay, 1 inch is very low height. 1 inch is a very low height. If I have a scale, I would have told you over here. Okay, very small scale, so I can make it here. Okay, 1 inch is this much. Okay, 1 inch. This 1 inch of uranium pellet is equivalent to 120 gallons of oil. This 1 inch of pellet is equivalent to 17,000 cubic feet of gas, natural gas. And this 1 inch of uranium pellet is equivalent to 1 ton of coal energy. So you can understand the amount of energy that is present in this much small size of pellet. Okay. So here if we see, we are seeing here 10 pellets. Less than 10 pellets can power the average household for a year. That means if you have only less than 10 pellets, that to 10 inches. 10 inches is this much only, man, this much. This can, and a very less thickness, is can power your household for a year. Okay, so here they have given a data of the USA, because it is a data from the, like, this equivalent I have taken from the Department of USA Energy. So they said that they are generating around 2,000 metric tons of used nuclear fuel, and they can utilize 90% of its potential energy by recycling it again, by re-enriching it. Okay, so you can keep on re-enriching it and you can utilize it, reuse again in it. Okay, so this is a uranium fuel cycle which I wanted to tell you. Okay, so uranium, natural uranium is mined. Okay, then it is being converted into a form which is called in a form of a yellow cake. So this is kind of a yellow cake that they make. Okay, so after that, this yellow cake is sent to a enrichment plant where it is converted into gaseous state, which is converted into a gaseous state, because in gaseous state enrichment works very easily. Okay, so yellow cake is turned into UO2, uranium dioxide, and then a gas, uranium hexafluoride. Okay, so we convert uranium dioxide into uranium hexafluoride. Okay, that is a gas. By converting uranium into a gas, we can easily enrich it. Okay, so this gas is enriched to increase the amount of U235, because it is easy to enrich a gas than a liquid or a solid. Okay, so this enriched uranium hexafluoride is again converted into uranium dioxide, and it is made into pellets, which I told you, that black color pellets that you can see. Okay, so these pellets are being put into a rods, inside a rod, and then it is sent to a reactors. Okay, where they go the fission reaction, and after they get used up, they are stored in a power plant only under heavy water or under the water or underground, and we can use, and we can also utilize it in the future by re-enriching it, by reprocessing it, and until and unless we dispose them, we have to keep it at a very safe location. right? So this is a much more detailed diagram where you can see uranium recovery is happening, mining is happening, then after that the process of conversion and enrichment that is going on. There's this enriched uranium is put into the uranium dioxide, and this fresh uranium dioxide is utilized in the reactor. Okay, after reactor, against the spent uranium dioxide was sent to reprocessing facility, and again it is re-enriched, and again it has been sent. So you can keep on re-enriching it and reutilizing it. Okay, and you can even dispose of if you are not wanted to utilize it, because if you have a cycle which is not working on that, you can remove it also. Okay, so these are the important things that are being part of a nuclear power reactor. Okay, nuclear power reactor. Okay, under the nuclear power reactor we have a reactor core is there. Okay, reactor core is there where all these uranium pellet rods are being placed. Okay, so you can see here inside this reinforced vessel, nuclear fission reaction heats up. Okay, so inside this nuclear fission reaction happens. Okay, so this nuclear fission reaction increases the temperature of this place to up to 300 to 350 degrees Celsius. Okay, and here we have certain amount of water which is also kept over here, and because we know that at 100 degrees Celsius water boils and convert into vapors, but we keep the situation highly pressurized so that even at that high temperature water remains in liquid form. Okay, and here you can see this red rods that are there. These are called control rods. Control rods means, neutrons are very, very important for sustaining chain reaction, but we need to control the neutrons in order to prevent undue reaction that is happening. So these control rods are also being put place in order to reduce the amount of neutron that are reacting with the uranium. Okay, so neutron absorb rod carrying a lower to control the rate of nuclear chain reaction. So these controlling rods help in controlling the nuclear reaction. Okay, and these reds are called fuel rods. I told you, the pellets are there, right? These pellets, these are arranged in these rods, red color rods. Okay, then this is a primary circuit. There is a superheated water that circulates between the reactor and a heat exchanger. Okay, so there is a you can see here we have a water that is here that keeps on circulating. Okay, that keeps on circulating, and which is in the very superheated form. Okay, so this superheated water reacts with heat exchanger over here. Okay, so this water react with the heat over here and convert this water into steam. Okay, so heat energy passes from the primary to a secondary circuit. Okay, so this is a primary circuit. You can see here this is a primary circuit. From here the water is going, and here it is reacting and it is transferring the heat to a heat exchanger. Okay, to the secondary. So you can see here it is sending here to a secondary circuit where steam is there. Steam is running the turbine with high pressure water, high pressure steam, and here you can see this is connected to a generator, and generator is generating electricity like that. Okay, and the steam, the unused steam is get collected over here, and this water is further feed into the heat exchanger, and then this whole process keeps on going. So this is how we can sustain the chain reaction over here. Okay, so as I told you, these are the important components. Fuel, what fuel we utilizes uranium dioxide pellets that I will show you right now. Okay, in India we have a pressurized heavy water reactor which is utilizing the natural uranium fuel, that is uranium pellets for that. What is the role of moderator? Okay, moderators are the material which helps in slow down the neutrons for increased fission. Okay, so in India we utilizes either heavy water, that is called deuterium oxide, or graphite. certain design, that is advanced heavy reactor requires graphite as a moderator, and our pressurized heavy water reactor requires deuterium oxide as the moderator. So this moderator slows down the neutrons so that more and more fission can take place, so that they reduces the speed, they slows down the neutron. Okay, then controlling rods are also there, because we have millions of neutrons that are releasing. Okay, so these rods absorb certain excess of neutrons so that we can regulate and control the reaction. Okay, so in India we utilizes boron carbide as a controlling rod in various reactor design. Okay, then we have a coolant. That means the coolant is a fluid that circulate to transfer heat, like from a reactor core to a heat exchanger. This coolant is going to work to circulate the heat from one place to the other. Okay, so in India we utilizes heavy water also serve as moderator also, and heavy water we can utilize as coolant also. Okay, then pressure vessel, container holding reactor core and moderator as a coolant, that is called pressure vessel. Okay, we have a pressure vessel where we put fuel bundles and fuel rods. Okay, then steam generator is there, which converts heat from primary coolant into steam for turbine. Okay, so the heat that is coming from a primary coolant, that is heavy water, get converted into steam for turbine, and this turbine will generate the generator. Okay, so this is how the whole process works. Now you wanted to see the pellets. Okay, I told you here, you can see it is up to 1 inch pellet is there. This is a size of normal pellet of uranium dioxide. Okay, you can see these are the uranium pellets. So these uranium pellets are put on a rod. Inside a rod we fill this rod with these pellets. Okay, we fill these rod with pellets, and there are bundles of these rods are there. Okay, bundles of rods are there which are put in this concentric circles. Okay, you can put that like that. Okay, and these bundles you put inside a nuclear reactor like this. Okay, what you are doing? First, this is a pellet. You are putting these pellet inside a single rod. This is a single rod. Okay, so there are hundreds of rod that are joined together where these pellets are being inserted, and this is only one part of fuel bundle that we put it inside one hole of this reactor, and there are hundreds and thousands of bundles that are there which can go inside these rod. Okay, so this helps in generation of the reaction. So you can see here, these are the bundles are there, and we sometimes take out the bundle, like if this bundle fuel is spent. Okay, so we take out that. Okay, we take out that, and in place of here we put a new bundle, fuel bundle over here like that. Okay, so this is how inside the reactor we have this part that is working inside the nuclear reactor. So this is how the things things are being packed. Okay, this is how the things are being packed inside there. Okay, now I have already told you, but here I have given you a schematic diagram. What is happening? So reaction is triggered. Okay, so we have a sealed metal cylinder is there where uranium is there, right? Here, this is a sealed metal cylinder. What is that? This is a sealed metal cylinder. This is a sealed metal cylinder, which I already showed to you. This is a sealed metal cylinder where we have a uranium is there, and neutrons are fired at a uranium atom. Okay, inside that we fire the neutrons. Okay, so once the neutron hit these pellets, so there is a chain reaction that is going. Okay, so these uranium atoms start splitting into smaller nucleus, and chain reaction will sustain. Okay, and it will generate huge amount of heat that is needed for a next stage. Okay, what is the next stage? So water that is passing through a reactor vessel. I told you, here we have a water. Here you can see this is a water that is passing from here. Okay, so here the water is here that is passing through a reactor vessel. Okay, so here you can see this is the water that is passing from a reactor vessel. So this is heated around 300 degrees Celsius. So we know that at 300 degrees Celsius water gets evaporated, but we keep the pressure very high. We keep the pressure very high in order to keep the water at liquid stage. Okay, so we apply around 155 times atmospheric pressure to stop it from boiling. Okay, to stop it from boiling. So here the water will remain in a liquid stage, and this water will be carrying the heat of the reactor. Okay, then how the water is circulated? So a coolant pump will be there, coolant, heavy water will be there. This will circulate this hot pressurized water from the reactor vessel to the steam generator. You know, there is a steam generator, correct? Here we have a steam generator. This is a steam generator. This is a steam generator, or more specifically, here it is not there. Yeah, this is a steam generator. So this superheated water goes here to a steam generator, right? So the hot pressurized water flows through 1000 to a steam generator. Then a steam is created inside over. So here you can see the steam is started creating. Okay, so steam is getting created, and there is a pipe that is attached around the pipes. Okay, so this water is under much less pressure. So heat from pipes boil the stream. Okay, boils the stream, and steam energy is passed through a turbine which causes them to spin. Okay, so there is a shaft that is connected which is spinning 3000 revolutions per minute to a generator, and which is going to generate electricity for all of us. Okay, then this electricity is passed to a national grid and power lines, and then this steam is further cooled. Steam is further cooled, and this steam is further utilized in a heat exchanger for further get converted into steam, like that. Now we are moving towards the type of reactors. Okay, so we have discussed the basic functioning of a reactor right now. Okay, we have just now discussed only the basic functioning of the reactor. Now we will be discussing types of reactor that we are utilizing. So there are 5 type of main reactors are there. That is light water reactor. We have then a pressurized water reactor. Then we have a CANDU reactor. So this is being utilized in Canada. Okay, and then we have a sodium cooled fast reactor, and then we have a fast reactors. Okay, so let's see one by one what all these reactors are. So under the light water reactor, this is the most prevalent type of a reactor that we are having throughout the worldwide. Everywhere they are utilizing, because this is utilizing ordinary water as both coolant also and moderators also within the reactor core. Okay, inside the reactor core we are utilizing the coolant which is getting heated up. Okay, and the moderator which is also controlling the speed of a neutron. Okay, so there are 2 type of light water reactor, that is pressurized water reactor under this, and we have a boiling water reactor under this. Okay, so one is pressurized water reactor and one is boiling water reactor under this, and each have their own special characteristics are there, and have their own advantages, and they both have their own disadvantages are also being part of it. Okay, so what is happening with the pressurized water reactor? Okay, so under the pressurized water reactor we will have a core. Core means reactor core will be operating at a very high pressure. Okay, and here the water will be serving, normal water will be serving as both coolant and moderator. That means this will be acting like a moderator, where it will be also controlling the speed of the neutron. At the same time it will be also acting like a coolant, which will be helpful in transferring the heat from the core toward the heat exchanger. Okay, so high pressure water absorb heat from the reactor core. Okay, and this high pressure also prevents water from boiling. Okay, so hot pressurized water flow toward the heat exchanger, where we have a steam generator, and this transfer the heat which is at a low pressure. Okay, here you can see the reactor vessel is there. Okay, reactor vessel, and we have a pressurizer over here. We keep the water at high pressure in order to prevent them from to get converted to prevent them from boiling. Okay, so that remains in liquid form, and we then send this water to a steam generator, and the steam generator will run the turbine, and then here we have a condenser where we further convert the steam into liquid water, and then again it is feed into a stream generator. Okay, so this is how. So condenser cooling water will be there to take to the cooling lake or there. So there may be cooling towers are also there. You might have seen big towers like this. Okay, big towers are like this. So these are all cooling towers. Below that we have a huge pond of water that is being stored over there. Okay, so what is the advantages of pressurized heavy water reactor and the cons of the pressurized over water reactor? Okay, so first is the strong negative void coefficient. Okay, so this pressurized heavy water is having a negative void coefficient. That means if the water starts to boil, the reactor automatically cools down. Okay, so this is a very important safety feature, because here the coolant also serve as a moderator, and this will help in sustaining the chain reaction. Okay, then here we have done a secondary loop isolation. Okay, so here what will happen is that it is having a water that is separate from a radioactive primary coolant. You know, the water which is there in the reactor coolant, that becomes radioactive. So we have the secondary loop also, which contains separate water. So this obviously enhance the safety and also simplify the maintenance. Okay, so radioactive contamination also get reduced. Okay, so radioactive contamination risk to turbine and various equipments are mitigated. Okay, and proper procedure can happen. Then operational expenses are there. So if we go by their history of operational experiences, or what we are trying, whether it is workable or not, we have seen that it is easy to use, it has a advanced safety measure, and this is more and more efficient over a longer time. Okay, but there are certain cons are also related to it. So if we go by the cons of this light water reactor, the thing is that if there is any kind of pipe rupture, or if the pipe breaks happen, so there was a coolant leak that can take place, and this is so heavy pressurized water that it may also compromise with the reactor integrity, because 150 times more than the atmospheric pressure that we are providing. So it is a very high pressure that we are utilizing. Okay, so there is a necessity to have a backup system for cooling. Okay, in order to prevent any kind of core overheating, because the reaction is already going on the core reactor. So we need something which keeps our reactor cool properly. Okay, then limited fuel breeding. So we know that we rely on enriched uranium fuel. Okay, so if we have any kind of lacking in the capability, or we are not able to properly enrich the fuel or brew a new fuel or other thing, so this reactor will limit our electricity generation, because this fuel require enriched uranium fuel. So there is a need to breed new fuel, like, or we should have different type of reactor which depends on various multiple fuel sources. Okay, so this also has a issue regarding the long-term sustainability and susceptibility of the uranium supply shortage. Okay, now under that, under this only, what is that light water reactor? We have already studied the pressurized water reactor. Now we will be discussing regarding the boiling water reactor. Okay, so here boiling water reactor has a principle of direct power cycle. Okay, so here we are, water is passing through the core, boils at a not intermediate pressure level. Okay, the saturated steam exits the core and undergoes superheating before driving a steam turbine to generate electricity. So okay, so here we are not providing too much of pressurized heavy water. Okay, so here we are passing this water from the core boils at a very intermediate pressure level, okay, not very high, only intermediate. And this saturated steam will exit the core, and then it will further go superheating. After going to superheating, it will run the turbine, okay. So it is having the core inside the reactor vessel creates heat, so that there is a steam water mixture that will be created, where very pure water, or we call it as a reactor coolant, they will move upward of the core and they will absorb the heat that is generated by the core, okay. Then this steam water mixture will reach the top of the core, and they enter a two-stage moisture separation that will be there, okay, where water droplet, because moisture separation will be doing, so water will be removed and the steam is allowed to enter the streamline, okay. Then this streamline will run the main turbine, and whatever the unused steam will be there, this will be sent to the condenser, where it will condense and again condense into the water, okay. So this result water is pumped out of a condenser. There are a lot of pumps that are being there. This will be taken out from there, okay. And reactor core, which is having fuel assemblies, they will be cooled by the water that is circulated using power pumps, okay. So we have around 370 to 800 fuel assemblies inside the boiling water core reactor. So here you can see we have the reactor vessel, correct. Under that we have a water, which is, because of the heating of the core of the fuel, it gets converted into steam, okay. Steam plus water mix will be there. So here steam water mix will be sent over here, where there will be a separate vessel will be there, which is separating the moisture, which will be separating the moisture with steam, okay. Moisture will be sent to the condenser again, and it will be separated out, and the steam will be utilized to run the turbine, and then the unused steam will be also sent to a condenser, where it will be further converted into water, and this water is again feed into the as a coolant into the reactor vessel, okay. This is a boiling water type of a reactor. So what is important in this whole process? So under this process we can see that this is highly cost efficient, okay, because it reduces the maintenance cost, okay, and it makes us economically attractive because it is very, very simple and it has a faster construction time, okay. And this also offer flexibility in adjusting power level by regulating the speed of jet pumps, okay, right. And even it provides a quick response time in electricity demand without compromising any kind of stability, okay. And 1 year of operation has already been so these are being reactor that are being utilized at various places. And if we see this has led to a very, very important design feature, because this is the easiest way in which we can run a reactor. As you can see that here we do not require much of the system. Most of the thing is happening inside the reactor core, okay, with the help of a water, and then we are utilizing it and condensing it. So this is called as one of the simplest model. But yeah, it poses safety challenges, okay, because there is a both liquid and gaseous water that is present, okay, inside the core reactor. So there is a huge complex issue that it can create, okay. So we have to find out, the safety analysis has to be done in order to find out, like, if there is any breakdown happens, so how we are going to provide a proper coolant over here, okay. So we have to understand and how we can mitigate these critical changes and criticality in our coming future, okay. Then there is a radiation exposure risk, because there is a direct contact of the primary coolant and the turbine, okay. There is nothing like that we have a secondary circuit or a primary circuit. So here the direct power, the water that is the primary coolant is running the turbine, okay. So this is directly reaching to the turbine, that radiated water, and then we are only getting that water converted into a steam, and that steam is running the turbine. So this is a potential radiation exposure hazard risk that is there. Okay, and if any kind of fuel rod leak happen, it may lead to radiation risk into the water, and then water will get collected at various other places over here. Okay, so maintenance has to be required, trained working professionals has to be kept, and also we have to understand the complexity behind this whole process. Okay, then fuel dependency and breedability. Obviously we are relying on the uranium fuel over here, and which we cannot breed new fuel. Okay, so that is why if proper uranium shortage has not been covered, so these reactor will become useless in the coming future. So we have to make sure that that we should make a reactor in such a way that they should run a wrong way, or either we can increase the supply of the uranium. Okay, so there is a need to explore for alternative fuel cycle. Fuel cycle means any other fuel cycle which we can utilize, so that our this stage fuel is utilized in the next stage also. So India has a three way process. India has a three stage nuclear program. Okay, so the product of stage 1 will be utilized in the product of stage 2, and stage 2 product will be utilized in the stage 3. So this is how we will be maintaining our nuclear cycle. So this we will be studying in the next lecture. Okay, then here there is a vulnerability to station blackout events. So this boiling water reactor has a issue of blackout events, like you might have seen in Fukushima, that has happened in 2011 when they have a tsunami in Japan. Okay, so there is a issue of a blackout that has happened. So we need to maintain the core cooling and power supply even under such condition. That is very, very important, because sorry, if the core is not getting cooled properly, and if proper power supply is not there, the reactor will melt down, and melt down will release huge amount of radiation into the nearby areas. Okay, so in our country right now, boiling water reactor is utilized in Tarapur Atomic Power Station in Maharashtra. Okay, so obviously since this design is very, very cost effective, cost efficient. Okay, so we are able to generate much electricity with the help of this boiling water reactor. Okay, but yes, obviously safety concerns are still there, and we need to focus on more and more stringent safety measure, and we have to keep on doing safety assessment periodically. Okay, and we should, since we are relying on imported uranium, and we have to focus on generating our own resources, otherwise our boiling water reactor will be much more vulnerable to the supply of uranium, because if the fuel supply of uranium get disrupted, we will not be able to generate long-term energy security for ourselves. So that is why we have India has a 3-stage nuclear program. Okay, now we have a CANDU reactor. Okay, so this type of reactor was developed by Canada. Okay, right? So CANDU stands for Canada Deuterium Uranium. So here we are utilizing deuterium, or deuterium is also called as heavy water. This act as reactor neutron moderator. Okay, so this is a very, very important things that we are utilizing. Okay, so this reactor also uses different from other reactor, because this reactor utilizes natural uranium. All other reactor that we have studied, they were utilizing enriched uranium, but this CANDU reactor is utilizing natural uranium as it is. Okay, so around 15% of this electricity of Canada is produced around that, and with 19 are in operation. Okay, so this CANDU reactors are also utilized in China, South Korea, Romania, India, Pakistan, and Argentina, where we are utilizing natural uranium. Okay, so fuel bundles of each bundle, like fireplace log means a log of wood. Okay, so this is being utilized, and this a fuel bundle will be able to provide electricity for a Canadian family for for up to 100 years. That means each fuel bundle can provide electricity for each Canadian family for 100 years. Okay, so CANDU reactor utilizes natural uranium, which we have already discussed regarding the all process of enrichment. But yeah, because natural uranium, we have U-238. So U-38 is fertile and can absorb high speed neutron and convert to the plutonium, which is fissile and undergo fission, right? So here we are utilizing the natural uranium. So what is happening over here is that if we see, the fuel will be in the form of uranium oxide powder. This powder is packed into pellets and placed into the fuel rods. Okay, and then this fuel rod is put into the cylindrical fuel bundle, which I have already told you. Okay, around 50 centimeter, they have a 50 centimeter in length. This much is the length of each fuel bundle. Okay, and they are 10 centimeters in diameter, this much. Okay, and they can provide, and they will remain in reactor from 6 to 24 months depending on which location and within the core. Okay, so that means if you put like this fuel bundle, they may work for 6 to 24 months over there. Okay, now moderator and coolant. So whenever we are utilizing the natural uranium, this has a totally different way. Okay, because the reason that the uranium does not need to be enriched over here. Okay, and due to heavy water moderator, which does not absorb as many neutron, and the commonly used light water does. So here what we are utilizing is heavy water as a moderator and also as a coolant. Okay, because we are utilizing heavy water, because normal the reason is that why uranium does not need because here we are not enriching the uranium, right? So is due to the heavy water moderator, which doesn't absorb as many neutron, and the commonly used light water does. Okay, so moderator work, we all know that it is used to slow down the neutron and also to reduce the obviously to reduce the speed of the neutron, so that they do more fission reaction inside the reactor. Okay, and this moderator is also kept at around cool temperature of 70 degrees Celsius as compared to the other temperatures, and there is a separate cooling mechanism for the moderator that is also being there. Okay, and heavy water is utilized as a coolant in CANDU reactor. Obviously heavy water is utilized, which will be acting like a coolant, and this coolant will be used to transfer the heat from a core reactor to the steam generator. Okay, so here you can see, this is how the fuel loading machines are there. Here the fuel is loaded. Okay, and then we have a heavy water is there, the steam generator is over here, and the steam generator is connected with a turbine. This turbine will be running the generator, and here cool water flows, and again it will be utilized. This water will be further utilized. So here in the CANDU reactor, we are utilizing natural uranium. Okay, powdered uranium is put under the pellets and then stored over inside this. Now what are the pros of CANDU reactor? Okay, minimal uranium enrichment. This is one of the most important advantage, because it requires very little enrichment or no enrichment. So further it reduces the cost and complexity of this whole process of fuel fabrication, right? Then we have a continuous refueling capability is there. Okay, so this reactor can be refueled while in operation. It is not like that if we wanted to refuel, we have to shut down the reactor, and then we have to do the refueling, and then we have to restart. Okay, so it will provide uninterrupted power generation. Okay, so without shutting down, this power can be maintained consistently, and you can refuel it from outside. Okay, so there is the fuel flexibility. They are highly adaptable. CANDU reactor are highly adaptable, and they can utilize various type of other fuel type and various type of recycled nuclear fuel and thorium also they can utilize. Okay, now then some of the cons, that is disadvantages of using the CANDU reactor, is that they have a positive coolant temperature coefficient. So positive coolant temperature means sometimes the coolant temperature becomes very high. Okay, so it further raises the safety concern. Okay, so if there is an increase in the coolant temperature, obviously it leads to reactor instability. Okay, so positive temperature coefficient has to be reduced in order to have a robust safety mechanism has to be put in order to prevent any kind of overheating that is happening. Okay, then whenever the reaction and fission reaction is going on, obviously neutrons are getting produced. So neutrons are being absorbed by the deuterium, that is called heavy water, and once the neutrons react with heavy water, it produces tritium. Tritium is a radioactive, and even a small quantity of leak further causes environmental and safety risk is there. Okay, so advanced stringent monitoring and proper containment measure is needed regarding this whole. And obviously there is a proliferation risk is there also is there, because there are various reactors are there. If we go theoretically, it allow you to produce weapon grade plutonium also at a very faster rate compared to the conventional reactor. That means it produce weapon grade plutonium at a faster grade. Okay, so this raised the huge concern regarding this proliferation. So these are some of the cons related to the CANDU reactor. Now we have the next reactor, that is called sodium cooled fast reactor. So here in the sodium cooled fast reactor, this is again a very important technology. So here we are utilizing liquid sodium metal as a coolant. Okay, and why we are having this word fast over here? It is related to the velocity of the neutron that we are utilizing in this reactor core. Obviously the neutrons are very fast in this whole process. Okay, so in this design we can utilize metals also, oxides and oxide fuels also. Okay, so this we can utilize various type of fuel option in this. Okay, so here with this sodium cooled reactor, here we are just only changing the coolant, which is we are utilizing the liquid sodium. Some places we are utilizing heavy water, here we are utilizing liquid sodium. Okay, so sodium fast breeder reactor have ability to breed their own fuel. Okay, that means they just keep on working and they keep on producing their own fuel, own fissile material, like they are getting converted fertile material like thorium into fissile material. Okay, so that means they are creating some other fissile material which will be utilized in the next cycle. Okay, so sodium fast reactor will sustain self-sufficiency fuel cycle. We don't have to keep on providing fuel, and we don't have to depend on any other for our own fuel cycle. That means they have a long-term stability. They have an ability to breed their own fuel. Okay, so this is a very so in India we have a prototype of fast breeder reactor where we are designing to breed plutonium from uranium-238. Obviously we are utilizing that. Okay, so this will further provide us with fuel self-sufficiency. Okay, then waste utilization. You know, in the nuclear reactors we have lot of waste, and that too radioactive waste that is coming, and that radioactive waste has to be managed properly, otherwise it will create catastrophic environmental damage that it can create. Okay, so sodium cooled or sodium fast breeder reactor have a very important solution. Here radioactive waste get converted into lesser hazardous isotopes, and the whatever the waste is created, they is further utilized as a fuel. Okay, so this will reduce the burden of long-term storage. Otherwise, if one time the fuel is used, you have to store it at some place. But here in this cycle, it has a self-breeding capability, so it will further convert it into a fuel which can be utilized in the next cycle. Okay, so here is an example of integral fast reactor IFR, which is utilizing which is aiming to efficiently consume nuclear waste as a fuel. That means they wanted to convert nuclear waste as a fuel. Okay, so that they should reduce the wastage and they can further increase their nuclear cycle. And then we have a passive safety feature is also there, because the use of metallic fuel and the superior thermal property of sodium, it will help in passive safety mechanism. Like if any type of problem or any malfunction or shutdown that is happening, the reactor can safely shut down without reliance on active cooling system, okay, or any kind of human intervention. Automatically the reactor will stop down, okay. So this is how it is going to work. But there are certain cons are also there, because sodium is a highly reactive metal. If sodium is exposed to air, it automatically catches fire, okay. If sodium is exposed to air, it automatically catches fire. That is why sodium has to kept in kerosene, okay, so that in order to prevent the contact with the air, okay. So sodium is a highly reactive with air and water, okay. So that is a huge challenges, okay. If slight leak of sodium is happening or slightly leak from the coolant system is happening, it lead to the sodium fire, because sodium will come in contact with air, okay. So it sometimes become very difficult to extinguish, and it may damage the reactor component, and further it has a cascading effect. If you know, Monju reactor in Japan has experienced a sodium leak in 1995, okay. So because of that, long-term prolonged shutdown has happened for that, okay. Then reprocessing requirement, like to fully utilize the fuel and manage waste, sodium fast reactor have to be necessitated reprocessing facility, okay. So if we are sending anything for reprocessing, it has a proliferation risk, okay, because at a place of reprocessing they may get diverted to a extent of a weapon grade plutonium. They can also try to make that fuel as a weapon grade plutonium, okay. So there is a process that is called plutonium uranium extraction process, which is commonly used in nuclear reprocessing, okay. So in this process we can separate plutonium suitable for nuclear weapons, okay. So these reprocessing facility has to be further scrutinized every time, okay. Proliferation risk is always there if not carefully controlled, okay. We know that neutrons are getting generated in the nuclear fission reaction, okay. So neutrons are needed for fuel breeding and fuel and fission reaction, but if you are not controlling it properly, these neutrons could be diverted to produce weapon grade plutoniums also, okay. Because we also have to check whether the reactor is utilized for what purpose, okay. So there is a need, and we have to check these fast neutron reactor, because in the past they have all raised the concern regarding the diversion of fissile material for military purpose, okay. So we have to keep on check regarding what is the use, or after spent fuel that they are doing, the countries are doing with the after the spent fuel, what they are doing with the spent fuel, okay, what they are doing at a processing facility, where they are keeping all these things. So this is all has to be kept at a proper scrutinized way, okay. Then we are coming into the fast reactor. What are these fast reactors? So what is the role of fast? Right now, whatever the reactors that we are discussing here, we are trying to reduce the speed of neutron, right? We are trying to reduce the speed of neutrons, right, with the help of a moderator to slow down the speed of neutrons. But in the fast reactor, we are keeping the neutron moving quickly. Fast reactor keeps their neutron moving quickly. That is why this name as the fast breeder reactor, okay. So these fast neutron will further unlock the energy of the dominant isotopes of U-238. You know, right? We cannot utilize 238, right? So we have to enrich 238. We have to enrich 235 U-235, okay, because maximally we are having this as a natural. Okay, in the natural uranium, the maximum isotope is used 238, and just 1 minute. In natural uranium, we have maximum dominant isotope is 238, and then isotope is 235. Okay, so this is maximum. Okay, and this we are utilizing in nuclear reactor. So with the help of a fast breeder reactor, these fast neutron will unlock the energy that is stored in U-238. Okay, so this will further enhance our fuel resources by around 200 times, because now we will be utilizing that natural uranium isotope of U-238. Okay, we know that the normal speed of neutron is around 2200 meter per second, while in the fast neutron might be cursing at 9 million per second, that is 3% of the speed of light. So we can further utilize these natural isotope of uranium for fast reactor. Okay, so this will, what is the advantages of that? Obviously it will enhance the neutron utilization, because it will further fuel the cycle, will further primary fuel the cycle. Okay, so again it will further enhance the sustainability of the nuclear cycle. Okay, we do not require U-235 always. Okay, so 200 times the process will increase, right? Waste reduction will be very, very less, because it will be capable of destroying any long lived nuclear waste. Okay, because this reactor will transform into less harmful waste. Earlier that are decaying in the century, and that will be decay in century, because nuclear waste takes millennia to decay, but with this process in the fast reactor it will decay in century. Okay, so this will further reduce the environmental impact. Then there will be more superior safety measures will be there, because we will be utilizing liquid metal coolant such as liquid sodium, which we have just now discussed. Okay, so with this liquid sodium, this will further increase the efficiency of the heat transfer. Okay, further increase the efficiency of the heat transfer, and this natural transfer will enable heat removal even any kind of severe accident is taking place, and this will further enhance our safety. Okay, so natural circulation will help in all this process. Okay, then metallic fuel options are there. Okay, so fast reactor can employ metallic fuel instead of oxides. Okay, because it will having much more higher thermal conductivity. Okay, and it will also have a safe shutdown without exceeding the temperature property, right? But there are certain challenges, because if we are going for fast breeder reactor and high fast breeder reactor, we require high startup fissile atom requirement. During the starting, we have to provide this fast reactor with 3 times more fissile atoms, so that these neutrons should get certain atoms to get fission over there in order to initial startup. Okay, initial startup करने के लिए हमको ज़्यादा atoms starting में चाहिए रहेंगे, because in the thermal reactor we were having low startup only because of small neutrons and small atoms we start the reactor. But here in the starting we need, in order to properly work on that, we in the starting we need fissile atom, more fissile atoms we require. Okay, then faster time scale. So operation in fast reactor occur at a very faster time scale, because fewer delay neutrons are there. Okay, so there will be quicker and unprecedented changes can also be expected. So we don't know how the reactor is going to respond. Okay, so that is why we should need certain robust control mechanism if something goes out of control. Okay, then sometimes there is a coolant instability. Okay, so bubbles in the fast reactor coolant, they may induce a positive feedback loop. Okay, so because of that, reactor may start heating up instead of cooling down. Okay, so because positive feedback means the reactor will start heating up, and if you have a negative feedback, it will start cooling down. Okay, so these are issues are also there regarding the coolant, because the bubbles that are there in the coolant may create a positive feedback loop. Then exotic coolant requirement. Okay, so in order to maintain the neutron velocity, we should rely on certain other new coolant requirements. Okay, like liquid sodium or lead bismuth utric, these are all needed. Okay, so we have to depend on certain other coolant which will further enhance our reaction in this fast reactor. Okay, so this will further increase the prices and operational cost and complexity of the fast reactor. So this is all a reactor, a fast breeder reactor. Then we have a sodium cooled reactor, then we have a Candu reactor is there, then we have a boiling water reactor, then we have a light water reactor is there. Okay, then we have already discussed all the things related to how uranium enrichment works and everything. So in the next class we will be discussing the advantages, policies, government nuclear policy, civil nuclear deal and everything. So till then, thank you so much. Bye bye, take care and have a good day.